This is the libhal bi-weekly meeting, and it is January 7th, 2025. So for the agenda today, we're actually not going to go over any new libhal 5.0 features. I'm actually going to go over a couple of things that have been updated recently, and we'll be going over the implementation and usages, or the usages of the CAN 5.0 interfaces, because I've actually backported them to 4.91. Now, the first things first, this doesn't actually have its own slide, but previously STM32F1 V4 and V5, forgot to include that as well, did not have GPIO 0 to, it only had 0 to, I think, 3, and now we have 0 to 8. So we have the full set. For input pins, and we also have like that. We have also expanded it for all the other pins as well. We don't have interrupt pin supported yet, so that's not there yet. And yeah, the rest we'll go over in a sec. So first we're going to go over shift left and shift right for bit masks. So I ran into this issue where there was a mask where the set of masks were all the same in a register, except one was in the first 16 bits and the other one was in the second 16 bits. So like same types of masks, same positions, just off by 16 bits. And it was part of a single 32-bit number, and I wasn't sure if I really needed it, but I wanted to be able to do basically this. I want to be able to do this here, and I couldn't. So I added support for it, and basically it works as such. So you can create any arbitrary mask, and you can shift it to the left or to the right. In contrast, which you would normally have to do if you wanted to do something like this, would be to create your mask like from 0 to 7, and then create the mask. I forgot to add in the HAL bitmask part here, but basically you'd add HAL bitmask here, and then you do positions equal to mask1 position dot 8, or I'm sorry, plus 8. That would shift you to the right 8 bits, and you keep the same width. And this example, this is pretty much just ripped straight from the unit tests, and all of these succeed. Same thing happens with shift right. One thing about shift right though is that it saturates, meaning that you can't have negative numbers for your position. So if you were to shift to the right and it would result in the position being 0 or less, it will clamp at 0. So you cannot go beyond 0. Shifting to the left though doesn't really have a bounds. It has the bounds equal to how big the position variable can be. So just keep that in mind. It's kind of unbounded to the left, but it is bounded to, it's not bounded to the left, it's bounded to the right though. And this is made available in libhal util 5.4.0. All right, so next up, we're gonna go over the proper ClayD query driver. So I've updated the user guide for VS Code and how to get it set up. The query driver that you should have on your machine should be --query -driver equals **/ g+, so on and so forth. Here's the whole story behind this. I actually spent some time before Christmas, some time after Christmas, some time between that to New Year's. Actually, I think I figured this out near the end, near the end of Christmas, or near end of Christmas Day. Basically, GCC needs, in order for ClayD to work with GCC, it needs to ask GCC where its includes are and other information about the compiler. In order for Claim to work though, allowing it to do that sort of introspection ends up resulting in some issues. Specifically, Claim for some reason on Mac provides way too many system includes, and some of them that it provides you, like, oh, here are paths that are places that we may look for includes, ClayD will assume that they're all actual paths that do exist that it will look for stuff in, and then it'll fail because it'll find out that that path doesn't actually exist. So those are really like options. And the part of me thinks that, ClayD should be able to go through that list, and for any folders that don't exist, just simply ignore them. But maybe I'll make an issue for that. I did communicate with them on their forum to ask them about help for this, and they actually gave me the help that I needed. So big up to them. This expression here is built to only accept G++ or variants that have the dash in front of it, like ARM, none, EABI, dash, G++. So in order to ensure that clang D works on all of your repos, I recommend doing this. And I don't think I've changed it yet, but oh no, I think I might have. But if I haven't, there's a change to the .clangd file, which basically just says the compilation database is in the current directory, and that's all you have to put in there. Nothing more than that. The one that we had before with the if-else statement was broken, did not work, and was ignored by clangd. I spent a lot of time learning how clangd works and how to get verbose output, so I could actually do some debugging. But yeah, that's pretty much clangd query driver. And now to our main thing, using CAN 5.0 in 4.9.1. So 4.8.0 had something that I realized was a bit of a problem. So I ended up breaking it in 4.90. Since I was the person who added these changes and I didn't think anyone else was going to be using them, we don't have that many users right now, I just went ahead and broke this without making the breaking change to 5.0. I don't want to, this was not worth it. This being clean here was not worth it in the fact that it would result in a lot of extra work on everyone's part if I broke the API and moved up to 5.00. So broke the API here in order to fix some things. But yeah, 4.91 is where you want to set your version for libhal to get the best version of this. So I'm going to show you what it kind of looks like to use the CAN 2.0 code. So first things first, the include for that's considered for STM. That's just kind of the same. Nothing changed here. Before it was just HAL STM32F1 CAN. Now it's CAN Peripheral Manager. I talked about this a little bit before, but I want to start having this idea of a driver object that is able to manage and distribute out resources. And the reason why is because there are a lot of things that have a limited number of specific resources. And because of that, I want to be able to express that better. And I find that this might be a better option. So this class doesn't actually inherit anything, but you can use it to acquire other objects that inherit or implement those interfaces that we would want. And then you use those objects. So here, the only thing that it really asks for is the baud rate as well as the pins you want to use. In this case, PB9 and B8. Next up, we want to create a transceiver. Transceivers allow us to send messages and also allow us to scan through the set of received messages and see if there's any that are useful to us. So we create a static array for received buffer messages. So this, in this case, we can store up to 4 messages received over the bus. We pass that over to acquire transceiver, to the CAN's acquire transceiver function, gets us back a transceiver object, a full object, not a reference to an object. This is the full implementation. That's why I use auto here. Otherwise, I'd have to write out the full name. We make that static as well because we're just going to assign it into some resource by address. Do note that the receive buffer must outlast the lifetime of this object here. These are bound to each other. Next up, we'll acquire a bus manager. Bus manager allows you to do things like go bus on, or if you become bus off. It allows you to set up an interrupt if you have gone bus off. It also allows you to control your baud rate. So that's all managed by the CAN bus manager. It is its responsibility. And then finally, we have an identifier filter. Now, the way that the STM has a large number of CAN filters. And because of that, and the filters are between mask, identifier, extended mask, and an extended identifier. I think it has, well, not super important. So there's actually I'll explain it. I think there's around about either 10 or 12 or I think 16, I forget the exact number, but there's a certain number of these identifier filter registers. And a lot of them can support up to 4 things. Like for example, when you acquire an identifier filter from this CAN profile manager, it doesn't actually return back it returns back an identifier filter set. Within it is this filter object. and you can get one out of it. So it's like an array of 4 for an identifier. So for each one of these functions you call, which uses up a resource inside of the can, if you keep calling this, eventually it'll throw. But let's say you only call it once, you'll acquire one of the resources. That gives you 4x the number of filters. So then we can pass into this, and then we can use it later on. Just a quick recap. We created a object that manages our resources. We were able to get certain things out of that object, such as transceivers that allow us to send messages and look at our messages. We can acquire a bus manager, which you can only have one of, and that allows you to control the bus. And you can also get a set of identifier filters to be used for whatever purposes you have. Each one can support a single message. Next up, let's consider what it would be like to kind of construct a driver using these. So here we're considering the libhal actuator RMD DRC driver. We would extract out a clock, a CAN transceiver, the CAN bus manager, and the identifier. Now in this case, we just need to set, we only need to use the CAN bus manager to set the baud rate to 1 megahertz. Otherwise, our DRC motor won't be able to respond because we won't be talking at the same rate. Here, we don't pass in the bus manager. That's not the responsibility of the DRC to be managing. We pass in a transceiver to give it the ability to send and receive messages. We also give it a CAN identifier filter, which allows you to basically allow messages from the servo back. So in this case, the messages that we send with this address are received by the servo, and then it will respond with the same exact address. The MC devices upgraded this to use different addresses so that there wasn't any sort of conflict. So let's take a bit of a look at the constructor for DRC v2. And actually, before we go here, we'll go here. So it takes a CAN transceiver, an identifier filter, a clock, gear ratio, device ID, and a response time. These are, I think, this was default set to like 1 millisecond, I believe, or something like that. An internal object, a member variable, gets default initialized. We have this thing called mcan, which takes the CAN transceiver and the device ID. I'll explain what this object is later on, but it basically allows you to find messages. We need this clock to be able to figure out timeouts in the future. We need the gear ratio to know how far what a degree is, and then we have a maximum time we can take between receiving a response. Now, the only thing we do with p-filter is simply say allow my device ID, and that's it. We don't store it, we don't keep it. P-filter shows up nowhere here. We don't need to bind ourselves to the filter. All we need to do is get a filter and say, hey, I want you to allow this particular address, and then let it go. What ends up happening next is now we're gonna call a couple of commands. Now we'll do system control off, and then we'll do system control running. Now off doesn't actually like turn the thing completely off. What it does is it kind of puts it into low power mode. Then we go running, and that re-enables it so you can actually control it. This has to send a message, it has to receive back a message. If this was somehow wrong or the device isn't present, then this will throw an exception. And that's what it means by commands will throw if device does not respond. Here's a bit of a look at the member variables. So here's just like what you'd see in the header. We have a CAN message finder, and that is mcan. And that's what takes the CAN transceiver and a device ID. Now, before we go any further, I'll show you how this guy works. The main idea here is CAN message finder needs the CAN transceiver to look at its buffer and its current cursor position. Like it's going to look at like the buffer and where the right head of the buffer is. So it's always going to need access to to the transceiver here. So we could have had a HAL transceiver, CAN transceiver, PM transceiver here, a pointer to it, as well as this, but that would just be an extra pointer that we'd have to save, which wouldn't be that useful. So the solution here is to have CAN message finder take this transceiver, hold it, and then if you ever need it, you can use a getter. And we try to make it inline so that the caller doesn't actually have to pay the cost of a function call. It'll just get the internal value directly out. And yeah, that's pretty much that. So what this particular driver does, or what this particular class does for you, is this. So we're going to go over a little example to show you how you can use it. So we're going to send a message. We're going to wait for a response. So here's our message. We have a payload. We know what our ID is, what the ID that we stored. You can actually get the ID from mcan as well. So you can use .id to get the ID you're trying to find. Our length is 8, and our payload, we're just going to assign it into the payload here. We're going to copy it into this payload here. We're going to use mcan transceiver.send. So this gives us access to the transceiver. We can then call the send function on that transceiver, pass it the payload, does the thing, sends it out. Here we're using the HowFutureDeadline function. You can pass in a clock as well as a amount of time that you have. And what it'll do is it'll calculate what the frequency is of the clock and the amount of ticks each, how much time each tick of the clock is. And it'll use the response time, or the number that the time that you gave it. It'll come up with the number of ticks would designate a deadline in the future. So this while loop kind of explains it. So long as the uptime is less than the deadline, or the deadline's greater than the uptime, so we haven't reached the deadline yet, run this loop. In this case, we're just going to poll. The time is relatively small, so I don't think we need anything like a IO waiter here. I think the time is in the span of like, what might I ever measure? I think it's like 10 microseconds or something like that. It's very fast. It responds really quickly. So if auto const message, basically what we're going to do is we're going to do mcan find. What find does is it checks the transceiver's cursor to see if it's moved, and it checks it relative to its previous cursor that it's seen. And if the cursor is moved ahead, it'll go and check all the entries from the time, from the point it's at up to the cursor head. It'll check to see if there's any messages that fit the mcan ID. If there are, then the result will have a message set. This is actually an optional. And then you can pass this particular optional into a function called handle message. And this is internal to RMD's code to hand that message. And after that, we just leave. If for some reason we get past this deadline, we throw an exception saying that we timed out. And that's pretty much it. That's pretty much a kind of short explanation of how to work with the CAN transceiver and how to kind of work with the drivers. From now on, what I'm going to try to do for as many of the libhal 5.0 drivers, I want to backport all of them. I'm actually going to go all the way to the front just so I can show you. Almost all of these here I can backport. There are a couple of these that are just hard errors, API breaks. For example, using a uint32 for clock and baud rates for things, I can do that for new stuff, like PWM group frequency and like PWM duty cycle 16. Like I can use these proportional values and all of that. But I can't drivers I'm going to dispose of don't matter. But in some areas, Hertz is just going to represent Hertz, and it's going to be float until 5.0. But things like ADC 12, 16, 24, 32, DAC 16, etc., SPI channel, PWM group frequency, and PWM duty cycle 16. I plan to bring those over. I don't know exactly when, because I don't think they're like very hyper necessary right now. Definitely will come in with 5.0, but at some point we will work on that. I guess another thing to add in is that I am currently more actively working on the USB side of things. It has been an absolutely exhausting experience, and I can't figure out why it was working before and why it's not working now. Typical experience in firmware, but I'm hoping to make some progress there so that we can build up our USB stack. I think we can solve that problem and do a lot of amazing things as well. For those who are in the actual Discord and in the meeting, I'm going to go over some of the other cooler things that are happening in the background. So for everyone else who's watching online, have a good rest of your day. Also, Happy New Year. And yeah, talk to you in the next 2 weeks.